Welcome back, infrastructure admins. Today, we are building your ultimate exam prep blueprint to master node imaging for the NCP-MCI 7.5 certification. In this explainer, we're going to completely demystify how to generate those critical fallback images, the strict storage space rules you've got to follow, and a massive architectural shift in recent AOS versions that is practically guaranteed to show up on your test. We've got a highly structured syllabus for you today. We'll start with the why, walk through CVM and foundation VM generation, uncover the exact exam traps that catch people off guard, and finish up with the key facts you absolutely need to memorize.
All right, let's jump straight into Section 1, the why, context and stakes.
Let's quickly baseline our core acronym so we're all speaking the exact same Nutanix language. We've got AOS, the Acropolis operating system, which is the core software running your data services. AHV is the Acropolis hypervisor, Nutanix's native hypervisor layer. The CVM is the controller virtual machine running on every single node. And ISO stands for optical disk image, basically the self-contained file with our software payload. Now, I know this sounds super basic, but under the immense pressure of an exam, mixing these up in a convoluted multiple-choice question is a really common pitfall. Knowing exactly what each component does is your absolute first line of defense.
As an admin, you already know that sinking feeling. It's 2 a.m., a node suffers a catastrophic hardware failure, or maybe a firmware upgrade goes totally sideways, leaving a host completely stranded. When normal cluster operations are down, you need a surefire bare metal way to get a hypervisor and operating system back onto that hardware. And that is where the Phoenix environment comes in. It's your ultimate fallback. It's a lightweight Linux-based environment you boot into via an IPMI console, and its entire purpose in life is to install AHV and AOS onto bare metal. When you're in Phoenix, you are literally at the foundation, ready to rebuild from the ground up.
Moving right along to Section 2. Let's walk through CVM ISO generation, specifically looking at the methodology and some incredibly important space rules.
Okay, so if you have a healthy cluster but need to image a stranded node, using an existing healthy controller VM is for sure the most efficient way to generate your Phoenix ISO. The CVM already has the tools, but pay really close attention here because the test writers love to trick you on the exact storage constraints for the CVM's home partition. Building an ISO takes workspace. If you're creating an ISO that only contains the AOS bundle, you must have exactly 13 gigabytes of free space in the CVM's home partition. But if you're bundling AOS and a hypervisor like AHV together, that requirement jumps up to 15.5 gigabytes. Why the extra 2.5 gigs? Because the hypervisor binary has to be fully unpacked and bundled alongside AOS during the process. Do not mix those two numbers up on test day. So the crucial point here is following the exact sequential steps to make sure your CVM doesn't just crash while building the payload. Step 1 is verifying you have that 13 or 15.5 gigs of space. Step 2 is actually checking it in the field. You SSH into the CVM and run the command df-h/home. This gives you the readable free space. If you're good on space, you hit Step 3. Navigate over to the foundation bin directory and run the generate_ISO Phoenix script, tagging on the flags for your specific packages. But wait, what happens if you run that check and you only have, say, 5 gigabytes free? The script's going to fail. The exam wants to know that you can use a specific command flag to route that ISO generation to a temporary SSD directory. You just create a temp directory on one of the CVM's mapped SSDs, which usually have tons of space, and add the flag --temp-dir equals followed by the path to that new folder. But here's a massive real-world operational tip. The system doesn't clean this up automatically after it builds the ISO. You absolutely have to go in and manually delete it to reclaim your storage.
Which brings us to Section 3, Walkthrough. Foundation VM generation, your offline alternative.
So what if a healthy CVM is totally out of the picture? Maybe you're deploying a highly secure dark site with zero network access, or the whole environment is down. That is when we boot up a standalone foundation VM. It's a prepackaged appliance you grab from the Nutanix support portal, run it locally on your workstation, and essentially do the exact same thing. You download the AOS and HV binaries, upload them into the standalone VM, and run that same generate_ISO script. It's the exact same logic, just happening in a sterile, offline environment instead of a live cluster.
All right, brace yourselves for Section 4, Exam Traps and Edge Cases. Welcome to the danger zone. Listen, the exam isn't just going to ask you basic commands. It's going to test if you know how the architecture has shifted over time. So pay close attention to this major AOS 6.8 change. The AHV ISO is no longer bundled inside the AOS installer. Historically, they came packed together. But starting with AOS 6.8, Nutanix separated them. Standalone AHV strictly comes in its own ISO format now. So if you run your script on 6.8 and expect it to magically find the AHV binary buried inside the AOS tar file, it's going to fail. You have to explicitly provide it.
So where do you actually find it? Well, as a brilliant failsafe, a copy is always cached locally right on every single CVM in your cluster. Even though it's not tucked inside the installer bundle anymore, a perfectly compatible copy of AHV is sitting right there. If you need it, point your KVM flag to /home/Nutanix/data/installer, then your enterprise Linux release directory, and finally /AHV. The exam will absolutely expect you to know that this localized cache exists, why it's there, and exactly how to map to it.
Here's another huge exam trap, and it's all about the ISO_whitelist.json file. Foundation validates Hypervisor ISOs exclusively by their MD5 checksum. It never validates by the file name. Never. A lot of admins think the system just reads the name like ahv-dvd.iso and says, okay, good to go. No way. Anybody can change a file name. Foundation calculates the mathematical MD5 hash of the file and checks that unforgeable cryptographic signature against the whitelist. If the MD5 doesn't match, it rejects the image, period.
Let's do a quick pop quiz to test your attention on that exact trap we just discussed. If you're on a CVM running AOS 6.8 and your generate_ISO command fails to include AHV, where exactly on the CVM do you look to find that natively cached hypervisor image? Think about it for a second. You are looking in the home/Nutanix/data/installer directory, into the specific Linux release folder, and finally into the AHV folder. Boom, that's where your perfectly matched ISO lives.
And that leads us perfectly into Section 5, Key Facts to Memorize, your final cheat sheet. You've absorbed all the concepts and the reasoning today, but these are the 3 absolute most critical facts you've got to lock into your memory for test day. Number 1, the space rules. 13 gigs in the home partition for just AOS, or 15.5 gigs if you're packing in AHV. Number 2, the architecture shift. As of AOS 6.8, the AHV ISO is divorced from the AOS bundle, but a copy is permanently cached in the CVM's installer directory. Number 3, validation. Foundation does not care what you name your file. It exclusively uses the MD5 checksum against the whitelist.
I really hope this explainer has totally armed you with the exact knowledge you need. By grasping the why behind these space constraints, the 6.8 architecture shifts, and that strict MD5 validation, you aren't just memorizing, you are truly mastering Nutanix infrastructure. Stick to this blueprint, and you are going to crush the node imaging section of your exam. But before we wrap up, consider this. If MD5 checksums are what protect our hypervisor installations at the bare metal level, how exactly is that kind of cryptographic security scaled across your entire cluster's storage fabric? Think on that, and we will unpack it in our next explainer. Keep studying, and we'll see you next time.